music that we created day before yesterday for this stream, and I'm bored of it, so I'll change and we'll create some new music. We'll keep the 10 but first we undo this and we save a copy. We save a copy because we probably will use this music in some video in future, so we don't want to just to waste some work. Yes. Okay, let's now wait, what happened? Stream music. Okay, let's come back to stream music. We are live. Let's delete all this. Select all, delete. Let's turn this off, turn this off, turn this off. And we play this. So some tam shake. Let's play again. That's how it'll start. I don't think so. Okay, let's whenever I do this, I just do some random that's nice. Okay, let's take that and let's put it here. Wait, come back here. One more. Can't it just go forward? Dude, can I just copy all this? Dude, relax. Okay, I have to do this. Control C, Control V. Hey, Sukhdeep Kharbanda, look at this. Look at this chat box. Okay, I created this chat box yesterday because this is like an empty space. Okay. Okay, this is how the music sounds. Okay. See, just random things. Okay, bongo low. There is some interesting instruments here. Conga low. So we add some conga low. You know what I'll do? I'll just create the first two. What do you think, Sukhdeep? Oh, it needs some work. Let's be honest. This is not. It's too much Congolo. Sorry guys, this is not actually a music stream, so if you're trying to learn how to play music, well, I mean, I'm doing the same too, so join me anyway, but I'll fail miserably. This will take a lot of work to sound good. let's just add some egg shaker and Congo mute and some bongo low. Alright, I think this is a nice confusing rhythm for some nice confusing session of music. Let's just go. Alright. And just yeah, let's continue. Okay, thanks, Sukhdeep. We will continue to the purpose of this stream, which is to play some brilliant.org puzzles. So today's Tuesday, June 16, the Great Candy Mix-Up. Below are 2 jars of candies with 1000 red candies in one and 500 green candies in the other. Let's say we take 200 red candies from the large jar, thoroughly mix them into the small jar, and then take 200 random candies from the small jar and put them in the large jar. Which jar now has a higher concentration of the candies it started with? Keep reading to find out, or jump ahead to today's challenge. Let's think about it. 2000 red, 500 green. We take 200 candies from the red jar, put it into the green jar. So it has 500 green and 200 red. Then we take 200 random candies. If we are taking it randomly, the odds are that the most expected answer would be about 2/5 of that. 40 will be red and 160 will be green, right? Because it's 2:5. 200 is to 500 in the small jar. 200 red and 500 green after the first step. So when we take out 200 random candies, again 2/5 of those, which is 40, would be red and 160 would be green. So we put back those in the big one, which jar now has a higher concentration of the candies it started with. Okay, so does red have a higher concentration of red? Or green has a higher concentration of green? We took out one. There must be an easier way to solve it, but instead of just brute force mathematics, but there must be some intuition here. Let's think about it. There are 500. Out of 500, we have... Sukhdeep, first of all, can you hear me properly with the music? Alright. So if we are taking the same amount of candies from the big jar and putting them in the green jar, and then taking again the same amount and putting it back, so 160 red candies are in the green jar, and similarly 160 green candies are in the red jar. The exact same numbers, exactly, right? That's right. Because we take out 40, but 160 is a higher percentage for the green than it is for the red. So red has more left of red. So red is the answer. After all, it looks something like this. Yes, let's say we end up with X red candies in the small jar. We know that each jar ends up with the same number of candies it started with, so those X candies must have replaced X green candies. It means there must be exactly X green candies in the right jar, and both jars have been equally contaminated by other color if we only consider the number of wrong candidates. Again, the same that we discussed. So the number of wrong candidates is the same, however one is half the other. So small jar has been affected twice as intensely as the large jar. So for example, let's say the large jar, so okay, all right, so we will correct. Any questions, guys? Any questions? Alright, today's challenge. Jar A has 800 red candies and jar B, yes, we were correct, Sukhdeep. And jar B has 600 green candies. If we do the following, move 1 cup of red candies from jar A to jar B and mix. Move 1 cup of mixed candies from jar B to jar A and mix. We already figured out that this will, if we are taking out 1 jar, this will create the same number of contaminated absolute contaminations, like the absolute number of contaminations will be the same. Move 1 cup of candies from each of jar A and jar B to the bowl and mix. Okay. Randomly select 1 candy from the bowl. This is interesting. This is interesting. This is interesting. So we do the 4 steps. What is the third step? We take the same amount of candies from A and B into the bowl and mix. Alright. So I would presume, since all the numbers are equal, right? We have the percentage. Wait, no, this is. Wait, no. So, okay, considering what we learned from the previous question, there are more reds in green than there are greens in red. Percentage wise. So when we take the equal amounts, the greens would be less in those mixture, right? The green would be less because why? Well, why? Because the percentage of reds in green, going by the number of red candies over green candies, red would likely go. Yes, I think you are right. Difficulty seriously serrated. What is that? It's 4 out of 5. I think it's red. Because what we have learned from the previous one, the contamination of green is higher. So more red candies come out of the green part than green candies coming out of the red part. And when we take out equal amounts, more red candies end up in the bowl. Yes. Okay. I feel happy that it's 4 out of 5 when we solved it. Thank you, Sukhdeep, for giving me confidence. Featured course algebra. So today, instead of buying a premium account, we will always have a 20% off, I think. We will start with some scientific thinking. Okay, we live in exciting times. I keep telling people that we live in exciting times. Is that a good thing? We should be living in boring times. Science is part of our culture more today than ever before. Black holes, rocketry, and quantum computing are all fields of advanced science that have made their way into YouTube and news and pop culture. But if you want to learn more about science, then you can get from the news clipping. The last 1,000 years of scientific ideas stand between you and mastery. Hooray! This sounds so promising. The puzzles in this course. Yes, like exactly. Little too exciting. Just a little too interesting. We want some simpler times. The puzzles in this course will start to bridge that gap. Wow. Wow, there is a bridge. You'll develop physical insight while you play, from gears to electric circuits to laser tag. You'll find scientific principles where you least expect them. I I'm kind of sad that all these tools are not available to like younger me. I, I'm just thinking about all the possibilities of people who have it now. It's awesome. We've all had one of those satisfying aha moments while poring over a crossword and finding the right arrangement of Sudoku numbers, or considering the logical plight of knights and knaves. We have done that. Knights and knaves, remember? Knights always tell the truth, and knaves always. Puzzles present a challenge for your brain. They all have a simple structure and a clear set of rules for solving them. But in the course, we won't be solving problems involving general knowledge, simple arithmetic, or logical contradictions. We will be tackling puzzles from the natural world. This is exciting, really exciting. This I find really interesting. Maybe more interesting than yesterday's. I think yesterday's course also had promise, but more as a teaching tool rather than a fun puzzle course. You can't enjoy a puzzle unless you know its rules. Similarly, you can't really appreciate the world around you until you understand the rules of nature. The physical sciences are a study of these rules, whether it is in form of chemistry, biology, or physics. In particular, physics is more than just a part of the physical sciences. Unlike the others, it explains the basic building blocks of the natural world: matter in motion, forces, energy, heat, light, and time. Sukhdeep, do you think my latest video kind of is related to this statement? No? Physics of the reductionist. Everything follows these same rules. The world is beautifully connected by laws of physics that you will find in this course. Alright. Physics and wait, are they going to even ask anything? Okay, there is some question here. Physics and engineering are often said to be about precision and mathematics, but here we will dispense with both these tenets and search for something else. Physical insight. I love it. Exciting. Some insights. While mathematical analysis can explain the exact range of a 500 kilopascal fire hose at a 30-degree angle, kPa guy who don't know kilopascal, it's kilopascal. Pascal is a unit of pressure, which is force upon force per square inch. So Newton per meter square is 1 Pascal, if I remember correctly. So 500 kilopascal fire hose. I mean, the pressure of water is 500 kilopascal, which I think means a lot of force at a 30-degree angle. The precision gained by specifying all the variables pays a steep price in generality. What is he trying to say? I've just lost in kilopascals. While mathematical analysis can explain the exact range of a so-and-so fire hose at such and such angle, the precision gained by specifying all the variables pays a steep price. Yeah, generally, if you know all the numbers, you can only know one answer, and if you don't know anything, you can generalize it into one specific equation, which can be applied to any scenario. Is that what he means? Answering simple questions can become hard when you become reliant on mathematics. What happens to the range of the fire hose when it doubles in length? Okay, intuition. We go back to some intuition. What about when it is raised to the top of a ladder? Wow, okay. We have these interesting questions. This is taken a different route though. On a journey to physical insight, we need to start from scratch. When you approach an unfamiliar physics problem, you want to first learn the main ideas and the important rules at play. What is pressure, and does it change with the length and height of the fire hose? Only by answering these questions can you make new predictions about physics at play. Okay. This, I think quiz 1 is just telling us things about the quizzes to come. Look at this buffoon. You might be surprised to learn that a fire hose can be made as long as you'd like without any drop in pressure. That makes sense. But for every meter you raise the fire hose, the pressure of the water and its range will dwindle. This is a very interesting insight. That's why no matter how much water is going through the pipe, if the pipe is too high, the water won't come out of the pipe. That's why the higher you live, people think like the top floor must have a higher pressure of water. At first intuition, people think the 10th floor will have a higher pressure of water than the first floor because hey, it's closer to the tank, so lots of water. And then when all of the people have used from 10th, 9th, 8th, 7, 6, 5, 4, 3, 2 floors, they'll be using all the water. The first floor will have the least pressure, but that's exactly the opposite of what the actual pressure is. The pressure on the first floor is going to be very high compared to the 10th floor because the height from which the water is falling. That actually has happened in my house, in my home. Someone plumber came and told us that the water pressure is going to be high, and my mummy said, we are on the first floor. And yes, science of pressure. I think we need to install some smiley back. Okay, anyway, let's come back to these ideas and rules structure your understanding of the problem. Precision isn't important and neither is mathematics. I love it already. Intuition is what I wanted to have. Physics, intuition and mathematics and sciences. Intuition, not the actual numbers, but intuition behind what is a sine wave, what is intuitively. That is more exciting than just equations. It's easier to refine this intuitive understanding than it is to create the fully formed mathematical analysis. This course will show you how to build insight and understanding first. Yes, Sudhi. This course will show you how to build insight and understanding first. You don't end up getting lost in number crunching. As long as the water flows frictionlessly in extremely long hoses, friction may have a noticeable effect on the pressure. We don't consider that. The thinking involved in solving puzzles is a unique blend of following rules with imaginative association. Only by combining both can you see a pattern or a twist that the puzzle conceals. If all goes well, you're able to use that hidden insight to form new information and ideas. What does that mean? The process will be exactly the same with physics. We bring the rules, you bring the imagination. Okay. Alright, I'm just a little sick of just reading all the rules. Let's go to the next. Is it not going to ask? Oh my god. Each year people spend millions of collective hours learning the rules to Sudoku, but to what end? After solving a few Sudoku puzzles, all we can say for sure that we learn how to play Sudoku inside everything. The rules are specific. The real world, so you know about the real world. How awesome. Our first, this is the worst episode ever. There's not one question solving. Sorry guys, skip this one, turn it off, don't listen. This is exciting actually. Our first stop is mechanical gearings. A lot of good science gets done without any deep principles. Very nice. Sometimes all you need are intrinsic things like how two objects touch or what shapes they have. This puzzle is one of those cases, and you can probably solve it with your intuition. The smaller gear has 10 teeth and the bigger gear has 50 teeth. When the smaller gear rolls around the big gear, how many times will the arrow return to its initial orientation? So teeth by teeth running around, for every 10 of these teeth, This guy, the smaller one, must have traveled one revolution, right? So 5 times. 1, 2, 3, 4, 5, 6. Return. Okay, so you shouldn't count the first one. 1, 2, 3, 4, 5. Actually 6. Wait, hold on. This is interesting. 1, 2, 3, 4, 5. Do you see it just hides itself? So that we get confused. Why 6? Wait, hold on. Why 6? Wait, okay. Now, okay, this is awesome. This is fascinating. Why 6? I think I know why 6. If you are standing on the big wheel, then from your point of view, the small one has taken 5 turns, right? So if you're standing in the center of the wheel, you will actually see the arrow coming towards you 5 times. Let's see. 1, 2, 3, 4, 5, right? But you are not standing, we are looking from the ground. From the ground, the guy who's standing in the center has also made 1 turn. So from the perspective of the person on the ground, 1 turn is being made by the yellow guy, yellow gear. You see what I'm saying? Does it make sense? 6 maybe. Sukhdeep, you always agree. You're smarter than me, I think. Yes, 20%. Wow. I think we don't deserve to get right. The only reason we got it right was because we were patient enough to see that the arrows do not actually. This is a good question. Very nice. Very nice. The first question was what do you call it in cricket terms? A googly. A googly. The next stop on our tour is heat transfer. Was it? Okay, you need explanation. Let's go back. Wait, hold on. Can we go back here? Okay. Show explanation. Loading. On first thought, it seems like the arrow should spin 5 times. Exactly. After all, when the smaller gear rolls ground, 10 teeth will touch the ground every time it takes 1 rotation. It stands to reason that this is a beautiful animation. However, rolling the small gear around the big gear is not quite equivalent to rolling it on a flat ground. It's more like rolling on a belt whose end has been curved around and inserted into its buckle. Imagine the smaller gear sitting on the end of the belt. When it's looped around and inserted in a buckle, the looping caused the arrow to spin 1 full rotation. This same effect is at play with the gear. Okay, randomly shows explanations. Okay, if it's like not for everyone, not for the simplest ones, but if it's like a googly, we'll definitely go for explanations. Next up on our tour is heat transfer. Prepare to meet your first rule. All objects release heat in all directions. Okay, this is the first rule. I think we've done a video on this. All objects release heat in all directions. The video of about quantum physics starts with this. Like, the reason quantum physics came up was because things were not giving heat according to the rules of physics known at that time. Something was wrong. Emperor penguins live in Antarctica and form large huddles with up to thousands of penguins to stay warm. Up to thousands of penguins. Look at this happy penguin. Penguins on the outside are very cold, but they constantly shuffle so that each penguin spends a tiny fraction of their time on the outer edge. You think there are a few of them who never go out. They're like sitting in the center. Do you think that's the case with their technology? Okay, when the penguin is on outer edge, I think this whole quiz will be the last for today. When penguin is on the outer edge, are they any warmer than if they are standing alone? I think they are warmer than if they're standing alone. What do you think? Because the standing alone guy is releasing heat from all directions, but the huddled guy is, yes, they are warmer. Yes. You don't need explanation for that, right? That's easy enough. You've probably heard of Newton's laws, which explain the motion of most ordinary objects. One of Newton's great insights, known in any other circumstances, the Newton's third law, very nice law, is our next rule. You push something, it pushes back. One of Newton's great insights, known in any other rule: for every push, there is an equal push in the opposite direction. If you push a box to the right, you will receive an equal and opposite push from the box to the left. See if you can use this to figure out our next puzzle. The fire hydrant above receives water from the ground at high speeds and redirects it towards the right. At some point, the rusty bolts that hold it to the ground all break and the hydrant comes free. In what direction does the fire hydrant move? While the water is going this way, fire hydrant will go left. But also the water is going in this way, so the fire hydrant will also be pulled down, right? Down, up, and to why up? Why not down? Because the water is going in from the bottom, right? No, the water is going in from the bottom, which is the opposite of the. If it were going out, right, then it will go up in the lower. If it were going out from bottom, it would definitely push up, right? Exactly, right? But it's not going going up. It's not going down from the bottom. The water is not going down, right? So it should do the opposite. So not directly upwards. Why up? I don't think it's going up. I don't think it's going to go up. It's wrong. Awesome. Up and to the left. Okay. Show explanation. I think we need to. Why up? To figure out which way the fire hydrant will move, we need to figure out how the fire hydrant is pushing on the water. Before the water enters the fire hydrant, it's moving straight up. But after the water passes through the hydrant, it no longer has any vertical motion. This implies that the fire hydrant pushes down on the water. Oh, the fire hydrant is pushing down on the water. It of course has to push down on the water. Wow. Yes. But this is so strange. It means water is pushing up, right? But if the water would also coming out from the bottom, it would still be going up. What does that give you? I'm so confused. This has really made me Sukhdeep, I told you you're smarter than me, but this has made me really confused. I need some professor in front of me. What's opposite direction? Look at me, Sukhdeep. Think about this. If the just reverse the direction of the water flowing, maybe it doesn't do that. Maybe reversing the water does not reverse all the forces. If that is happening, then I'm wrong, of course. Let's see. We might not be able to solve this, but I'll come back tomorrow definitely. However, there is now that happening before the water passes through the hydrant. It has no horizontal motion, but afterward it's moving towards the right. This is the fire hydrant pushes the water to the right. By overrule the hydrant feels an equal and opposite push to the left. In total, the fire hydrant. I kind of understand their point. I get it. So the idea is, it since the water was going up but now it's not, it means it's being pushed down. So the fire hydrant is being pushed up. Since the water is also was not going horizontally initially, but now it is, so the fire hydrant is pushing it horizontally as well. So the opposite is okay. Now let's just reverse the direction of water flow. Let's say it was coming horizontally and now it has to be pushed down. So where are the forces on a fire hydrant? Fire hydrant has to push the water towards the right, okay, because it has to stop the leftward flow of the water, okay. So fire hydrant is pushing the water to the right and also pushing the water downwards, okay. So the forces are the same. Manu, do you get it? Oh my god! No matter the direction of the flow of the water, the forces are the same. Whiteboard. Oh, you can't see the whiteboard. I should add the whiteboard here. Something like that. Okay. The forces are the same. It's hard to explain. Yeah, it's intuitive. It can be intuitive. I see what you're saying. It is intuitive. But have you noticed this non-intuitive thing? Just reverse the flow of the water. It does not change the forces being applied by the hydrant. According to this explanation, the hydrant is pushing the water down and right, okay. If the water flow was opposite, it would have still been pushing the water right towards the right and down. This is crazy. Do you understand? Do you see what I'm saying? Right now, since the water is going up, then the direction is changed from up to right. The forces applied are towards the right and down to stop the vertical motion, and right to increase the right motion, right. Change the direction of the water flow to make it opposite. The water is going left and down. So if the water is going left initially, the fire hydrant has to stop that flow of water, so it's pushing it towards the right and has to push the water down. So it's in both. This is awesome. Thank you, brilliant Doror. There was this book that I loved called Surely You Are Joking, Mr. Feynman, where Feynman creates a pump contraption in his, like a thought experiment, like an anti-sprinkler underwater, and asks people what exactly is going. It's kind of similar to this question, and all right, that really stumped me. I really loved it. Thanks, Manu. Yeah, it's a brilliant one. I think if we continue this for a few months, and if we get some viewers, we can ask Brilliant.org to like sponsor us and give us money, some money. Guys, we are in this for the money. Ultimately, clearly, one viewer is not going to solve it. But let's see. our last rule on the tour is a little bit deeper. It isn't so much a scientific principle as it is a principle about scientific principles. Okay, principle about principle. No matter how we choose to look at a physical process, the outcome has to be the same. If a car collides with us from the right at 5 meters per second, the outcome is the same if we collide with the car from the right at 5 meters per second. Yeah, relative speeds. Sometimes all you need is a little change in perspective to turn a hard problem into an easy problem that you know how to solve. See if you can do that here. A train is barreling down the tracks at 200 kilometers per hour towards a bouncy ball that sits on a stand. After the ball and the train collide, how fast will the ball be moving? I think it will be moving at 200 plus 200, 400, more than 200. Why more than 200? Let's say. Why more than 200? Do you think it's more than let's take their advice and switch. Let's take their advice and switch. If the ball were moving left and it hit the train, from the point of view of the train, the ball is coming towards the train at 200 kilometers per hour, right? So from the point of view of the train, the ball should leave the train at 200 kilometers per hour, because you are the train. It bounces, it comes towards you at 200 kilometers per hour, so it has to go away at 200 kilometers per hour. But you haven't stopped. It's not like the ball stopped you. You are still going at 200 kilometers per hour, right? So you are going at 200 kilometers per hour. The ball also has to go away at 200 kilometers. So the ball has to be moving at 400 kilometers per hour. Isn't that what I said, Sukhdeep? It's more than 200 kilometers. Hint, what happens when a ball bounces off the ground? Correct. Do you want to see the explanation? Let's see the explanation. There are a few ways to look at this. The first way is to look at it from the perspective. I mean, initially you would think that why would it be more than 200 kilometers per hour, right? Right? Only if the train weighs the same as the ball and stops. The train stops. If it's like two balls colliding, one has the speed of 200 and it hits the other ball and stops, then the speed of the other ball will be 200 kilometers, not 400, right? But this one ball is like a million times the weight of the other ball, so that's not the kind of collision that we are looking for. That's why it will be 400. The first way to look at it from the perspective of someone standing on the side of the train, this is what we did. For the person, the bouncy ball is sitting at rest on a tee when it gets hit by a train moving at someone standing on the side. This is not what we did. The second is from the perspective of someone standing on the train. If we try to solve this problem as one of the Brilliant standard, we need to write down the total energy of the system and the total momentum before and after the collision. This would produce a set of equations that we could solve for final velocity. We could solve it, but that would be wasted effort. The problem is much simpler in the perspective of the train passenger. In the train's point of view, the ball approaches, bounces back. This is just like a ball would hit the speed 400 kilometers. All right. I like this website. This is not spoon feeding. This is not your run of the mill just feel good quizzes on the internet. It's really deep and I think it's worth it. I think I should get the premium and do this every day. You should get more viewers. We'll call someone once we have some more experience. Yes, this mind bending Sudeep. Do you think there is potential? Now you should have a better idea of the approach we are taking. Learning by doing. In this tool, we kick the tires on a few rules. If you missed some problems, khareed lo. Yes. Yes. Thanks, Manu. I will khareed lunga. But don't take once from the light chapter from the study of electricity these concepts in a house of mirrors. I love it, and with this we are at 11% in scientific thinking. I love this quiz. Today was the best one, and we'll premium. What is this limited thing? What is this? Okay, it's okay. Just continue with this. Whatever we are going. Okay. We'll continue with this tomorrow. Thanks for listening. Thanks for being there, Sukhdeep. And let's see where this goes. I find it very interesting. And let's hope we have more people listening to it. And let's see how we do that. Maybe we'll share it with a few friends who like puzzles. I know a few people who I used to do puzzles with. Let's invite them. And see you tomorrow, same time almost. Peace out, Sukhdeep. Cheers.